right. Good morning, folks. Happy Monday. Welcome to the third week of summer school. We're going to go ahead and get started with some announcements. So I'm just going to share my screen so we can take a look at this week's announcements on Canvas. All right. So in case you haven't seen this week's announcements, we are 25% of the way done with the class, which is kind of crazy. And this week we're going to be we're going to finish chapter 10 today. And then we're going to get through most, but not all of chapter 12 this week. You have quiz 5 that is due by 9:30 on Wednesday morning, and you have quiz 6 that is due by 9:30 on Friday morning. And then exam 1 grades are posted. They should be posted for everyone, I believe. And then I just wanted to remind us that exam 2 is on Tuesday, July 7th. So it's a week away. It's going to be not tomorrow, but a week from tomorrow. In talking to you folks over Friday and over the weekend in terms of exam check-ins, one of the things that some folks have said they might want to start trying, so I thought I would share this as a strategy for the class in general, is to be working on your cheat sheet as we kind of go through the unit. So after every day, whatever it is that we've learned that day, to take some time to summarize that onto your cheat sheet. So you're sort of building it as you go. And then when you go to study for your exam, you can always tweak whatever you have as you need. Okay, that was one strategy that came out of a few conversations. Another one that I thought was a great idea that we could share is that some folks have been looking ahead at the quizzes, so thinking about what is coming up on the certain days, because a bunch of the quizzes have already been posted, so seeing, okay, this is what we're going to cover Monday and Tuesday, this is what we're going to cover Wednesday and Thursday, and being able to sort of know what kind of questions you might want to ask in lecture before we actually get to lecture. Okay. So to those of you who took time out of your days to check in with me about exam 1, for me it was super nice just to chat with folks in a more one-on-one situation and get to know you as students. So that was super awesome for me. If you have not signed up for a check-in, the calendar option is still up on Canvas today. So I have a few slots today. If you are interested in meeting, you can go to the calendar part in Zoom, which I don't know what it looks like, or in Canvas, I don't know what it looks like for you, but over here for me, if you click on the calendar, it'll show you a place where you can just click on certain times that are available for a check-in, okay? All right, that's all the announcements that I have for week 3. Does anyone have any questions for me before we get started? So I'm gonna go ahead. Oh, a couple questions popped up in the chat. No, thank you. All right, thank you, folks. All right, so I'm gonna stop sharing this, and I'm gonna go ahead, and today we're covering 2 sections, all right? So that is gonna be, the first few weeks, I know it was very, very intensive. We were going over 1 section a day. The sections were very large and very full of different strategies and decision making. And so now we're sort of continuing to ramp up that pace, if you will. On Thursday last week, we covered 2 sections, 10.1 and 10.2. And then today we are covering another 2 sections, 10.3 and 10.4. So my hope is that we can do 10.3. We'll take a break. I'll stop the video. And then we'll come back and we'll do 10.4 in the second half of class. And if there are any questions on quiz number 5 at the end of class, I'm happy to take any questions that folks have. And so we're gonna go ahead and get started. All right. I don't know if this is a Southern California thing, but sometimes when the weather's not so great, my internet gets kind of weird. So if I'm lagging, please let me know. Or if you realize that I can't hear you, even though I'm supposed to be able to hear you, please let me know and we will troubleshoot as quickly as possible. I know the lag is really irritating on the student end of things, and it's not fun on my end either. So let's address that if it becomes an issue. Okay, so we're going to start here with 10.3. We're looking at integrals that have infinite limits of integration. Okay, and so today in the what we know and what's new, I left this blank on purpose because I want to take some time to draw some diagrams. Okay, and so we're going to take a look at what it means when we have something like this. All right, so we've seen a bunch of these problems in Calc 1 where we had an integral. And we had a number down here, and we had a number up here, and we had some function. And you could go through all the processes that you did. Usually it was U sub, or maybe even a more simple power rule, something like that. And you would take your integral, you would plug in your bounds, and you would get a number. And that number represents the area between the curve, so whatever your f of x is, and the x axis. Okay, so when we see that integral symbol, the number at the end, like it doesn't matter how complicated the integral gets, but that number at the end represents the area between the curve and the x-axis. And so just to kind of put a diagram with that, you could have a situation where you have your x-axis, and then you have a function, okay? And then you have a starting point and a stopping point. So you start at A, you end at B, and so if you found the integral of f of x dx from A to B, that number in this particular diagram should be a positive area or a positive number. Okay. But you might also encounter some situations where maybe at the end, the number that you get is negative. And all that means is that you had the x-axis and you had the function that was below that curve. And same thing, you started at a certain point and you ended at a certain point and you found that area. And if it's above the x-axis, like the first picture, it's going to be a positive area, but if it's below the x-axis and we're going from left to right, it's going to be a negative area. Okay. All right, so that's something that we should know, should be familiar to us. And I think, you know, one of the tough things about calculus is it's so conceptual that you go through this whole process and you're like, what am I even finding? All you're finding is the area, okay? And so what we're gonna take a look at today is gonna be some cases where we see something a little bit different, where we're gonna see maybe like the integral from A, but their upper bound is actually going to be infinity. So it's not going to be a number, but it's going to be infinity. And we have a curve. And so this is actually saying the same thing as what we know, right? So visually, it kind of looks like this. You've got your x-axis. You've got your function. Okay, but this time your A value is like a number, and then the stopping point is actually all the way out at infinity. And what we're trying to see is, can we find an area for this? Okay, can we find that area? Now, some of the questions might have infinity as our top bound, but some of them might have infinity, or rather negative infinity, as the bottom bound. Like maybe we're looking at the left end behavior of something. And so if we were to think about a diagram that might go with this one, we've got the x-axis, we've got a function, and we have a stopping point, but our starting point is just negative infinity. So before we take a look at any of the actual problems here, can someone tell me whether, like, what your thoughts are right now? Do you think that we can find an area as we go to infinity? And why or why not?
No.
No, why not?
Well, infinity is a bound listed, but it doesn't actually exist.
Okay, so you're thinking that we can't find the area. Okay, yeah, I mean, I think
a repeating factor or something where there's an exact number where it just continues, like pi or something.
Okay. Let's see, let's check out that chat. What other ideas? Wouldn't the area just be infinite? So it can be infinite area, and sometimes it can actually also have a number.
So I kind of think about it in the same way of the philosophical question that if like a turtle and like Achilles go to like, or covering half the distance each time, technically it's infinite, so you'd never finish the race, but you do finish the race. So that's kind of like what limits represent too, in a way.
Yeah. Okay. I like that analogy there. Someone in the chat said that if the function reaches 0, there'll be an actual limit. Okay. So one of the things that I think is really interesting about chapter 10 that you started to kind of experience on Thursday was like, it's not really as straightforward as we think, right? In our heads, we're like, well, we've just learned that for all these years that, a number divided by infinity is undefined, and now we're saying it's 0, and how is that possible? And so we're going to kind of continue that messing with the brain today, where we're looking at situations where, to clarify, these curves do not actually touch the x-axis. So even as we keep going to infinity or negative infinity, the curves don't actually ever touch the x-axis. They get super close to it, but they don't actually get there. So that's one thing to keep in mind. Okay, we're looking at a very distinct set of graphs where the end behavior is getting close to 0, but it doesn't actually get there. Okay, and in some cases, we're gonna be able to find a specific area, like a number that represents that area, kind of like this idea of that that turtle, I think you said, covering half the that distance every single time, and eventually they do get there. But then we're also going to have situations where we're not going to be able to find an answer. Okay, and so the question that we're going to be asking ourselves is, in these situations where infinity or negative infinity is one or sometimes both of the bounds, the question that we're asking ourselves is, does it converge or does it diverge? Okay. Converge means that we try a process and we're actually able to find a number. Okay, so converge means we get a numerical answer. Diverge means we end up with positive or negative infinity as our answer. And what it really boils down to is how fast does that curve get close to the x-axis? It turns out that if it gets close to the x-axis fast enough, we can actually have a numerical answer. Whereas if it doesn't get close to the x-axis fast enough, then that's the case where we end up with infinity or negative infinity as an answer. Okay. So I'll let that marinate for like a minute or two. I know it's not even 10 a.m. and it's like, whoa, okay. We were dealing with all these infinities and like negative infinities, and our question really is, can we find an area? Because is the curve dropping fast enough? Or is it too slow and we're not going to be able to find that area? Okay. So we're going to take a look at a couple cases today. All right. So I think there are 3 different cases that we're going to take a look at. And before we do that, let's summarize these 3 cases. Okay. So let's say that we have a function that is continuous. All right. So in this section, we're going to be looking at continuous function. So if we're looking at a function that is continuous along a given interval. So in the first case, we have from a to infinity. All right, so we start at a, we go to infinity. The way we approach this is, and someone mentioned it earlier, we are using the idea of a limit. So we're going to say that the area from a to infinity, we can approximate that using this limit as b approaches infinity and putting b up at the top. So we're replacing infinity with b so that we can take an integral, and then at the end we say, well, let's take the limit as b approaches infinity. And if we can get a number out, then we're good to go. That function is going to converge. But if we don't get a number out, we get infinity or negative infinity, then that means that function doesn't drop fast enough, no area. A second variation on this is the case where we have from negative infinity to b. All right, so that top bound is a number, but the bottom bound is negative infinity. So to do that, we replace the bottom bound with a and keep the top bound with b. And then at the end, after we integrate, we take the limit as a approaches negative infinity. And then the third case, we might have a situation where the interval goes from negative infinity to positive infinity, meaning the whole x-axis. So our bottom bound and our top bound both have infinite integration limits. So what we're going to do in this case is we're going to sort of break it up into case 1 and case 2. We're going to have the negative infinity to a certain number, all right? And we're going to talk about how we pick that number. It doesn't really matter, but we want to pick a number that is going to be easy for us to kind of move forward. And then we're going to split the second integral from that number to positive infinity. And then what we really have is case 1 and case 2. All right, so case 1 and case 2 help us create this third case when we're going from negative infinity all the way to positive infinity. Okay. All right. So let's move on to a couple examples and see what this looks like. So case 1, from a to infinity. All right, so we're looking from a to infinity. And so here's a little diagram to kind of help us out, okay? So if we look at the diagram first, this is very similar to what I drew earlier, where we have some sort of starting point, and then we want to find this area under the curve. And in the first picture, this is the stopping point. Like, we're stopping at a certain point. But what we're going to do is say that instead of stopping at that point, we're going to take the limit as it gets to infinity, and then we can see if we can get an area or a number that represents that area. That would mean it converges. Or can we not find an area because our answer is infinity? Okay. All right, so let's read through this text on the left-hand side. If the integral from a to t of f of x dx exists for every t greater than a, and it's greater because t is, we're moving towards positive infinity, so we want to move in that direction, then what we can say is the limit from a to infinity is going to be the same as the limit from t to infinity, taking the integral of a to t of f of x dx. Now, t just tends to be the letter that we use to represent like that upper bound that is not actually there. It's what we're going to replace with infinity later, okay? So a few vocab things. What we're dealing with is called an improper integral because one of the bounds is not numerical. So because one of the bounds is infinity, we say this is an improper integral, okay? Now it's important that our function is continuous over the given integral or interval, because if we skip some places, then we definitely can't find an area, okay? So the last two bullet points here are really hitting home, like, what are our answers going to mean? So if the limit gives you a numerical value, then we can say that the improper integral converges. And that numerical value represents the area between that curve and the x-axis over whatever interval we're looking at, okay? So in this diagram, or in this packet, I've included some graphs because I think as we're looking at these problems, it's important not to work just through the algebra, but also to make sure we understand, like, visually what's happening here, okay? So let's get started with this first example, all right? So I see the integral from 2 to infinity. That infinity is on the top. Oh, sorry. That infinity is on the top. So I know that it's going to be case number 1. And I have this function on the bottom, okay? Or on this, in the integral, 1 over x minus 1 squared. So let's think about functions we know, functions that are good to know, and what that minus 1 and things like that mean, all right? So this function, 1 over x squared, is a good function to know what it looks like. This function looks something like this. It kind of has like one branch here. It has a vertical asymptote, and then it has a second branch over here. That's just for 1 over x squared, okay? When I have 1 over x minus 1 squared, what does that minus 1 do to the function?
Was it right one?
It does move it to the right one. Cute. Yes, so this -1 is going to move my function to the right one. And so now I'm going to draw a larger picture so we can kind of see what's happening, okay? So I've got my x-axis, I've got my y-axis. I'm going to dot in the vertical asymptote this time at x equals 1, okay? And then the rest of the function still kind of looks like that volcano. Goes up, and then a second branch on the other side. Okay. So if we look at our integral, we are starting at 2. Okay, so the question asks us to start at 2 and then go all the way to infinity and see what that area is. So since I know that the vertical asymptote is at x equals 1, I know that 2 must be somewhere to the right of it. So that's my starting point. And I want to see, can I find this area as we go all the way to infinity? Meaning, does this branch drop fast enough, get close enough to that x-axis fast enough that we can actually find an area? In other words, does this converge? And so let's go back to our original problem and apply the formula that we saw above, okay? But before we do that, any guesses? Do we think that this is going to drop fast enough that we could find a number for that value, or do we think this is going to diverge?
Yes, it will drop fast enough.
All right, I've got a yes. Anybody else? All right, so let's find out. So what we're going to do is we're going to rewrite our integral, but in front of it, we're going to have the limit as t approaches infinity. Because we're going to swap that, we're going to keep the 2, but we're going to change the infinity to a t. And then we're going to have 1 over x minus 1 squared dx. Okay. Now, in order to take this integral, I'm going to need u sub, so I could say that u equals x minus 1 du equals dx. And so really, I end up with the limit as t approaches infinity of the integral from 2 to t of 1 over u squared, all right, or 1 over this u squared. And when I take that integral, I have to use the power rule, but one thing I just want to make sure that we all understand is that this is the same as u to the negative 2 du, right? So when we use the power rule, we have to see that power. We can't just use it straight from the bottom. So when we apply the power rule here for our integral, we're going to end up with negative 1 over u, or I'm going to put back in that x minus 1. And I'm going to plug in t, and I'm going to plug in 2. So I'm going to keep the limit out front, okay, while I plug in the bounds. So I have negative 1 over t minus 1 minus negative 1 over 2 minus 1. And let's clean this up a little bit, see what we get. I get the limit as t approaches infinity of negative 1 over t minus 1 plus, because minus and minus make it a plus, and 1 over 1 is just 1. Okay, so now let's plug in our infinity and see what we get. So I get -1 over infinity minus 1 plus 1. This, because I'm taking the limit as t gets to infinity, 1 over infinity is really 0. So I get 0 plus 1. And you folks were correct who said that it does drop fast enough, because at the end, after we plug back in infinity, or the idea of getting close to infinity, we're able to come up with an area. And so all this means is that this pink shaded area over here, starting at 2, going all the way into infinity, has an area of 1. All right, any questions on example 1? Okay. Let's move on to example number 2. Okay. All right, so I see that infinity on the top, and I know, all right, this is case number 1, right? So the location of the infinities need to be in certain places. But let's go back and kind of think about our graphs, okay? So if I asked us to say just f of x equals 1 over x, again, that's a good graph to know. That graph is going to look, that first branch looks kind of like the x squared one, but then the second branch is actually down in that third quadrant. Okay.
I do have a question
Yes, what's up?
about question number 1. So then we get 1. Is that the actual answer? That's gonna be our area?
Yes,
Okay, thank you.
you're welcome. Okay. So this x minus 1 on the bottom, okay, just like last time, that moves our function to the right 1 unit. And so if we sort of draw a larger picture of what that looks like, then we have a vertical asymptote at x equals 1. We've got a branch over here and a branch over here. And then we are starting at 2, just like last time, and going until infinity. All right, so that's what that question is asking us to do. Thoughts this time? Which function do you think drops more quickly? Example 1, 1 over x minus 1 squared, or example 2, 1 over x minus 1?
Example 1 drops faster.
Yeah, what makes it drop faster?
The exponent.
Exponent, exactly. The fact that it's squared on the bottom, such a small detail, but that means that it makes it drop faster, okay? So this one, let's take a look at what happens if we apply that limit. So we get the limit as t approaches infinity of 2 to t 1 over x minus 1 dx. And this coefficient for x is 1, so I have to use u sub, but it ends up being just a constant of 1. And the integral for 1 over x minus 1 is something we've seen a whole lot. That's going to be the natural log of x minus 1. And we're going to plug in t, and we're going to plug in 2. All right, we get the natural log of t minus 1 minus the natural log of 2 minus 1. Okay. And when I take the natural log of 1, I actually get 0. So that's a good number to know. And then I'm seeing what happens when I plug in infinity. So the natural log of infinity minus 1. And infinity minus 1 is effectively infinity. And natural log of infinity, if you think about the graph of natural log, it grows and grows and grows. It grows kind of slowly, but it keeps growing. So as t approaches infinity, the natural log of t minus 1 also goes to infinity. And so this function does not drop quickly enough. And in fact, that gives us an answer of infinity, which means that it diverges. It does not have an area. Okay. Does not have a numerical value for that area. All right. So let's take a look at case number 2. So case number 2 goes from negative infinity to b. All right, so we're looking at the left end of the function. Does the left end of the function drop quickly enough? Okay. And the answer is going to depend. So if we can apply this limit and we get an answer out, a numerical answer, that means that it converges, the improper integral converges, and that number represents the area between the curve and the x-axis, okay? Again, this is called improper because one of the bounds is infinity or negative infinity, and it's important that our function is continuous over the interval we're looking at, okay? All right, so let's take a look at example number 3, okay? So for example number 3, let's start off with a diagram of our function. So here we have e to the x, and that is one of our parent functions. It's an exponential function, good one to know. So let's sketch out our function. And e to the x is going to start pretty close to the x-axis, and then it crosses through 1, and then it goes up pretty quickly, all right? And so in this particular example, we want to know if we stop at 1, okay, that's our top bound, and we go all the way to the left to negative infinity. Does the exponential function drop fast enough so that we can find an area there? Or does it converge? All right. So let's check it out. We're going to start with the limit notation, the limit, but as t approaches negative infinity. And then we're going to take the integral from t to 1. Our function stays the same, e to the x dx. Okay. Now, e to the x has a really nice integral. It's just e to the x, not even any chain rule in here, just e to the x. And so what we're looking for is the limit as t approaches negative infinity of e to the x, and we're going to plug in 1, and we're going to plug in t. So that's going to give us the limit as t approaches negative infinity of e to the x minus e to the t. Or sorry, 1. E to the 1 minus e to the t. So e to the 1 is e minus e to the, let's plug in our negative infinity. What is e to the negative infinity? What does that go to?
0.
It does go to 0. How do we know that?
Infinity.
Because it's the same thing as like any number over infinity goes to 0.
Yeah, so this is going to go to 0, which means we really have e minus 0 or e. So this function, this improper integral, converges to a value of e. Okay, so we can say that it converges. And, sorry about that, and that orange area underneath that curve right there, that has an area of e, right? Kind of cool. You have this function that has a base of e to the x, and then if you find that area from the end of the function all the way to 1, that area is actually e. All right, let's try, we ready for example 4? All right, so let's give you guys a couple minutes to set this one up. If you're not sure what the graph looks like, you can throw it on Desmos, check that out, see what it looks like. Or you can go straight to the limit notation and kind of go with that part, okay? All right, so here's a rough sketch of these diagrams. In the quiz, I do believe I give you the diagrams, but in this case, I want to talk through maybe like some of the more common functions that come up and like how do we know what that picture looks like. This one I would say is a little bit less common, but you have a square root in the bottom, and so you know that the numbers on the inside of that square root can't be overall negative. Like 3 minus a number better be positive, otherwise we can't take a square root of that in the real realm. And so that's why there's no function on the other side of x equals 3. But what we're looking for is like, can we find that orange area or not? Okay. So let's take a limit as t approaches negative infinity and call that bottom limit t and the top one 0. And I'm going to rewrite this as the 3 minus x to the negative 1/2 dx. Okay. Now, when I take this integral, I need to make sure that I use u sub here. Okay. So I want to make sure that I do u equals 3 minus x because du is not going to equal dx. It's going to equal negative dx. That means that we have a negative du equals dx. All right, so we're going to gain a negative sign when we take our integral because of this. So after we do that, we're going to end up with u to the negative 1/2. So that's u to the add a power, and then the reciprocal of that. And then we're going to plug in 0 and t. And we need that negative sign that I said don't forget about. All right, so I'm going to bring the negative 2 out to the front. And then I'm going to plug 0 into my 3 minus x, okay? So 3 minus 0 to the 1/2 minus 3 minus t to the 1/2, okay? And let's see what this gets us. Negative 2 times the square root of 3 minus the square root of 3 minus negative infinity. That's going to give us infinity. And so I can distribute this negative 2 root 3 plus 2 root infinity. But at the end, this 2 root infinity is going to overpower that negative 2 root 3 part. And so we're going to end up with a situation where that improper integral diverges. Okay. So sometimes that function will drop quickly enough, we're able to find an area that we call converging, but sometimes it doesn't drop quickly enough, or maybe that bound is not working, and so then we end up with a case where it diverges. Okay?
Quick question.
Yes, sir.
On the quiz, if we come to a value like infinity or 3, we must write diverge or converge next to it, correct?
Mm-hmm.
Okay.
Yeah. Would we use L'Hopital's? L'Hopital's is when we're just looking to take a limit, but right now we're taking the limit of an integral, so that's not a situation where we use L'Hopital.
Professor, on the step before you plugged in the infinity, are we still supposed to write the limit as t approaches negative infinity on
Yeah,
that?
I would bring that limit down to that second step as well. Sorry. Okay. Any other questions? What happened to the negative on the infinity? It was 3 minus negative infinity. So 3 minus negative infinity goes to 3 plus infinity, which is where I got that infinity from. Okay, great. All right, so let's move on to example number 5, okay? And in looking at example number 5, let's take a look at what happens, okay? So I've got my bottom bound is negative infinity. And so this is going to give me the limit as t approaches negative infinity from 0 to t, from t to 0 of 1 minus 2x e to the negative x dx. Okay. Now, how do I take this integral?
By
Yeah.
part?
Exactly. We're going to need integration by parts here. Now, how do you guys know that it's integration by parts?
You see a function and not a part of its derivative.
Yeah, exactly. And in fact, we have two different kinds of functions, right? We have our polynomial and we have our exponential function, right? So we could actually use tabular integration here. Anytime your u is a polynomial, you can use tabular integration. And so let's set that up. I don't think we'll need that many lines, but our u is going to be 1 minus 2x. And so we're going to take that derivative. So 1 minus 2x gives me negative 2. And then I have to take my derivative one more time. I have to get to 0. Okay. And then my dv is e to the negative x. So when I integrate, I get negative e to the negative x, and then I get e to the negative x. Okay. When I multiply these, I'm going to keep the sign. And when I multiply those, I'm going to change the sign. And so this is going to give me the limit as t approaches negative infinity of 1 minus 2x times e to the, times negative e to the negative x. And then minus a negative, so plus 2e to the negative x. And we're going to plug in 0, and we're going to plug in t. All right, let's maybe clean this up a little bit before we plug in our bounds. So negative e to the negative x plus 2x e to the negative x plus 2e to the negative x, 0 to t. And so I'm able to combine some like terms. I get 2x e to the negative x plus e to the negative x, and I plug in 0, and I plug in t. When I plug in 0, the first term is going to go to 0, plus e to the negative 0 is not going to 0. Okay, so be really careful about when you plug in things, what goes to 0 and what goes to 1. Minus, we're going to plug in negative infinity, so negative 2 infinity e to the negative infinity plus e to the negative infinity. All right, so we've got a 0, e to the negative 0 gives me 1. E to the infinity is going to give me infinity. This is going to negative infinity. What are our thoughts?
Are we going to 0?
What do you mean, are we going to 0?
If we have 1 negative infinity, are we approaching 0?
How are you getting 0?
No, I just thought that if eventually we have 1 and then negative infinity plus infinity,
Yeah.
I thought that maybe we are approaching to 0.
Well, you're right. We have the 1 minus 0. How does that give us 0?
So are you allowed to combine the negative infinity plus infinity to be a 0?
Are you? What do you think?
I don't think so.
Okay. All right. So this is a good question, right? Like we have this negative infinity and infinity. Are we allowed to combine those? And from the first part, we have a 0 and a 1. So I think we feel fairly confident that that first part goes to a 1. And so what I'd like you to do today is think about this one a little bit more. Do you think this one converges or do you think it diverges? And we're going to revisit this question very quickly at the beginning of tomorrow's lesson. Okay. So we're going to leave this here for right now, but I'd like you guys to do a little bit of research and see, do we think this one converges or do we think it diverges? Okay. Okay. So we're going to take a look at this one last case where we have bounds that go from negative infinity to positive infinity. All right. And so in this case, both bounds are what make it improper. We have a positive infinity, we have a negative infinity, we don't have any numbers in there. And so what we need to do is that we need to split it into two different integrals, okay? And so we're gonna pick a value C that is between negative infinity and positive infinity, and C can be any number, okay? But what we're gonna need at the end is we're going to need for this integral to be convergent, meaning we can find a value for it, and this one also needs to be convergent. If only one of them converges, then the improper integral overall diverges. Okay, so you need both parts to converge. Like the left end has to drop to the x-axis fast enough, and the right end has to drop to the x-axis fast enough. Okay. So let's get a diagram for example number 6 and see what we're looking at. So this function, 1 over 1 plus x squared, it looks something like this. And so what we're trying to find out is, do these ends drop fast enough so that when I try and find the entire area underneath that curve, can I find it? Okay. So what we're gonna do, and it doesn't have to be the middle number, but I'm just gonna pick the middle number in this case. Like this graph is symmetric about x equals 0. So I'm gonna make my top bound for the first integral 0 and the bottom bound for my second integral 0. So that's going to give me the integral from negative infinity to 0 of 1 over 1 plus x squared dx. That's my first integral, plus the integral from 0 to infinity of 1 over 1 plus x squared dx. Okay. Now, in this case, all right, and this is not always true, but in this case, we have a symmetric function. So if I can find the left-hand side, I know it's going to be the same as the right-hand side. Okay, so in moments where you can use symmetry, I would go ahead and say, well, this is going to be the same as 2 times one of the parts. Because if I find half of it and I double it, then I'll get the whole thing. Okay, but you need to see that symmetry in order for that to be true. Okay, so we need to find out, does this one converge? And if it does, then the other side by symmetry is also going to converge. So let's keep that 2 out in the front. We're going to take a limit as t approaches infinity from 0 to t, 1 over 1 plus x squared dx. And I know that exam 1 had a ton of crazy integrals, but this one is one of our tried and true ones, right? We're not using u sub here, but we are looking for arctan. And so we're going to have 2, the limit as t approaches infinity of arctan of x, and we're going to plug in t, and we're going to plug in 0. And so that's going to give us 2 times this limit as t approaches infinity of arctan of t minus arctan of 0. Okay. Now this goes back to your unit circle, but an angle that has a y over x value of 0 is 0. Okay, so 0 represents an angle here. Whether you're in radians or degrees, it doesn't matter, but that second part's going to go to 0. But then what we have is 2 times the limit as t approaches infinity of the arctan of t. Now, if we plug in infinity, I know that looks really weird, okay? But let's unpack what this is asking. This is saying find an angle that has a y over x value equal to infinity on the unit circle. So maybe a better way to look at that is, where is tangent undefined? And tangent is undefined at pi over 2. And so this is going to give us 2 times pi over 2, or a final answer of pi. All right, so this whole green area right here, it has an area of pi when you go from the left end all the way to the right end. All right, so that's what we have for 10.3. I'd like to take a quick break, but before we do that, are there any questions?
I have 2 questions real quick.
Mm-hmm.
The first one is, how did we know that C was 0?
You can pick any number, but it could be like, you could pick 1, you could pick 2, you could pick 3, you could pick any number you want. 0 tends to be a nice number to pick because a lot of times it's easy to figure out. Like when you plug that 0 back in, it's gonna either get rid of a whole bunch of stuff or it's gonna make some stuff go to 1. So it's a nice number to pick.
Okay, got it. Thank you. And then my second one is, so in this case, is undefined, we see it the same as infinity if it's like the tangent we have here?
You mean like the arctan part?
Yeah, like when we saw that it was arctan of infinity, and then you said we have to find which angle is undefined. So that's like the same thing?
Yeah,
Okay.
exactly.
Thank you.
You're welcome. Any other questions, folks?
I don't have a question, but I think I missed some part of the answer on question number 2. Do you mind going back to question number 2?
Sure.
Thank you.
You're welcome. All right. Well, if there are no other questions, I'll leave this up on the screen, but it is 10:35, so let's be back at 10:40, so we can jump right into 10.4, okay?
One last question.
Yeah.
On that last answer, when we were taking the tan inverse, what's the range of tan inverse? Like, so I know that you pick pi over 2, but you would not want to pick 3 pi over 2, right?
No. You can look that up, what the domain and ranges are for arctan, arcsine, arccosine. But arcsine and arctan are from -π/2 to π/2.
Okay.
Yeah, we're looking really at like the right half of the unit circle.
Okay, and that would be the same for tangent, I believe.
Exactly. Yeah.
Okay, cool.